Limitations of Ohm's law. Now, Ohm's law, it is kind of a more generalized kind of a law which can be applied to any conductor. But there are certain limitations or there are certain restrictions where we cannot apply the Ohm's law, or there are certain devices which does not obey the Ohm's law. So, what are those? Before we get into that, in what conditions it comes or in what devices it comes, let us discuss about two things. That is, first is ohmic devices and non-ohmic devices. Any device, if it obeys the Ohm's law, then that device will be called as ohmic device, and if that device does not obey the Ohm's law, it will be called as non-ohmic device. Now, what are the examples? Ohmic device means it can be any conductor. You can take copper, you can take a copper wire, you can take an aluminum wire, you can take an steel wire. So, any kind of a wire which is made up of a metal, it will be an ohmic device or a ohmic conductor. But in the semiconductor electronics, we had studied about the p-n junction diode. That diode is not going to obey the Ohm's law. So, such a device will be called as non-ohmic device. If we have the Ohm's law, V is equal to Ri. This is my Ohm's law. Now, similar equation you have seen in mathematics in the first year as well. What was that? It was Y is equal to mx. Now, if you recall, this equation represents a straight line. So, if I have a graph and if I draw a line, if that line crosses that origin, then I can be writing it as y equal to mx. And if it goes from some other point and it touches a y-axis at some other point other than origin, then it will be y equal to mx plus c. Now, the same line can also be used to represent this Ohm's law. This graph represents the Ohm's law, and in this case, the x-axis represents the potential and the y-axis represents the current, and the slope of this line is going to represent the resistance, because y equal to mx, that m represents the slope of the line. In this case, that r, that is our resistance, is going to represent the slope of the graph. Instead of having this kind of a characteristic, when we were having the p-n junction in the forward bias, I had put the potential on the x-axis, current on the y-axis, same as this thing. But in that case, I had, instead of having a straight line, I had this kind of a curve. Now, in this, whether the slope is constant or not, just by observing, you can say that in this region the slope is less and in this region the slope is more. That means the slope is not constant. That means I am not going to get a straight line like this in this graph. That means this kind of a device will not obey the Ohm's law. So, what is happening here is the relationship between V and I is a non-linear. It is a curve. If it was linear, then it would be called as the ohmic device, and the device was obeying the Ohm's law. Whereas our p-n junction diode, what it is doing, it is giving a characteristic curve which is like a curve. It is a non-straight line. It is non-linear curve. Then in that case, we are going to call this kind of a device as a non-ohmic device, and there we cannot apply the Ohm's law. So, that is first limitation, that is the relationship between V and I is non-linear. The relation between V and I is going to be dependent on the sign of V. How it is going to be associated is, if I take the reverse biased diode, now according to the graph, whatever, when I applied the positive voltage it gave me this kind of a curve. If I apply the negative voltage, that will be on the negative x-axis, I should get a similar curve like this. But if I apply the negative voltage or the negative potential to the diode, then instead of giving this kind of a curve in the third quadrant, what it gives is something like this. So this is the graph when the diode is reverse biased. It will be giving a curve in the third quadrant, and if you observe the first quadrant and third quadrant, the way the current behaves is not same. It was going in a curved way, then this curve, this is also a curve, but the shape is totally different. So in this way, what happens here is when the voltage or the potential is positive, it is giving a different characteristic. When the voltage becomes negative, it is giving a different characteristic. So again, this is the second case where the Ohm's law fails. That is, the value of the current is dependent on the sign of the potential, that is V. Third one, relation between V and I is not unique. There are some devices, it is going to be something like this. If I have V here and I here, then if I take the value of I here, I can have this value of V, and at the same time I can have this value of V. So I will have V1 and V2. There is a single value of I, but there are two different values of V. That means the relationship between V and I is not unique, and this kind of thing happens again in this device, that is a compound semiconductor, that is gallium arsenide. It is going to give a characteristic curve which looks like this. Fourth condition is, again I will put a graph. What is my Ohm's law? It is V equal to Ri, and for that the equivalent equation what I had said was Y equal to Mx. If I get a C, instead of that line passing through the origin, it is passing at a different location. In that case also the Ohm's law is going to fail, and that kind of a situation arises in a particular setup which is called as water voltmeter. So in this case, it is not going to be passing at the origin. For a zero value of potential, we have some different value, for a zero value of current, we have a particular value of potential. So in that case, again the Ohm's law fails. So